I'm Andrew Wilson.
I'm the amazing Tall Casher,
And I'm Emily Baumstark.
who didn't use an adjective.
So the main objective of this project is to build a solar lighting system that's going to be used eventually in little villages in India.
Where there is no electricity.
Exactly. So to start off with the project, we obviously started with the objective, and then we started getting our supplies together. So some of the main things that we needed for the project, one would be a lamp, we needed a charging circuit, an LED, a solar panel, and a data acquisitioner using a program called LabVIEW.
So overall, the way this is set up is we take voltage in from our solar panel, and we have our charging circuit charge the battery, which is hooked up to an LED, and the charging is done through a USB port. So you can detach it, and if, say, the light is used to light a room, you can then take it on the go.
You can also use it as a flashlight, so if you can unscrew the top here and you can use it for close proximity lighting. And then with the charging circuit, there was a second group in our class that did work with the charging circuit, that they made one so that it'll connect straight into the solar panel, which will be given to the homes in India as well. This is verification that the heatsink we chose was the correct heatsink. The Sunny Buddy uses maximum power point tracking, which ideally draws as much current from the power source that the battery can handle. It pulls this current from the cell and uses it to charge the battery, and it also manages if the solar cell drops too low so nothing is damaged. Controllers with MPPT take the output of the solar panel and determine the current that they need to send to the battery in order to charge it. There are three methods. The first one is perturb and observe, and it adjusts the voltage by a small amount until it just can't increase the voltage anymore. This can result in power output oscillations, and that is a negative. The second is incremental conductance. In this case, the controller measures the change in the current and the voltage to determine the charge. This needs multiple computations, but it can track the charges quicker, and it also can have multiple oscillations and be erratic. The final method is constant voltage, which momentarily sets the current to 0 to determine the open current voltage and set the percentage to an approximation of 76%. This can cause energy waste and not always be trustworthy. However, it is low cost and simple to implement.
Figure 1 shows the basic charging of a lithium-ion battery. It shows us that as the voltage goes up, the current will go down. Figure 2 also shows the charging, but at the end, as it reaches the maximum voltage, the voltage will drop and then go back up because it is unsafe to charge a lithium-ion battery past its maximum capacity. Figure 3 shows the discharging of lithium-ion batteries. It shows the discharge down to about 2.3 volts, and we deemed our light no longer and completely off at 2.1 volts, so it should be a good representation of what we should see through our testing. Here we have our overall schematic. We have a solar panel going into the charging circuit, which goes into a USB that's disconnected, and that goes into the battery, which goes into a switch which controls if the LED is on or off. Okay, so the main building of this had to do with the lamp, and I just went out to Walmart and got a affordable lamp that was functional, that looked like it was pretty easy for us to modify, and it was really simple to use.
Yeah, so one of the main factors of this project is it obviously being cheap so that it's affordable in India. What we did to connect it from the charging circuit to the batteries, we used a USB connection, and we stripped back the data in and data out portion. So if you have the 4 wires for a USB, and we kept just the power and the ground.
All right, and so then for the modifications as to the lantern itself, for starters, we had to cut holes that would be able to fit the USB connection and the switch connection to the outside so that they would be usable. Also, when you unscrew the top, we had to take out the lamp that was already in there, and we also had to cut lines right there to make room for the heatsink that is attached to the back of the LED. So this is just so that the LED sits flat in our holding circuit and is able to be seen from the cover right here.
Okay, and so on the inside, underneath where the batteries were originally placed for this specific lantern, we have basically all of the wiring. So we have a makeshift battery holder that was made from battery terminal blocks and the springs and contacts that were originally taken out of this, and Tupperware and some hot glue. And you can see the insides where we have all of our wiring, and you can see the USB connection here, and then the back of the switch is here. Everything's soldered, and any exposed metal from us soldering is wrapped in heat shrink to make sure that no loose connections or anything can touch, so everything is safe. So overall, the modifications were really simple. To drill out the inside of it, we used a Dremel as well to cut these holes out. It made it easy and precise to get the sizes of the cuts that we needed.
We use LabVIEW to automate our test measurements. So all the data was taken initially as voltage differentials, and we have a VI with graphs for key real-time feedback while we're taking measurements in case we need to adjust anything or realize we did something wrong. And all the data was imported into Excel at 2 Hertz and 2 samples. So that means that you have 2 samples every half second. And using that, we were able to make timing in Excel. And so what we have here is we have the prompt asking a user for the input, and it'll store it into C users, and that's just a place we store it as a .xls file. So that's the Excel file, and then it goes into a conversion, which makes it a file path, and then it does go into a file, and we have the data acquisition going into the Excel file, and we have the indicators for key real-time data. Here we see the waveforms and anything for key real-time feed. Our goal was to have a charge and discharge of fully so we can map and take our data for that time frame. And so first what we did was we did a 1.8 hour study of an LED discharge and then an 8-hour study of a LED discharge. So we can see the instrumentation current, it starts at about 0.6 and then drops off to 0. And the voltage goes from 3 and then it goes almost linearly to 2.6, and the same with the battery voltage. Now during our second study, we had 3 volts, and interestingly enough, we let it run for 8 hours and it plateaued at 2.5. So we really realized the magnitude of these measurements, taking it on a larger time scale. To get our first real charging, we went up to the roof and charged the battery. Okay, so we've set up our solar panel test to charge up our battery up here on the roof of Swearingen. So we've got our solar cell providing what LabVIEW says right now is 6.3 volts, 6.6 volts into our Sunny Bunny charging circuit, going into an instrumentation resistor, going into the battery, and then the battery's coming back into the Sunny Bunny. So the solar panel is charging the battery right now, and we're taking a couple of different measurements. The first measurement is the voltage of the solar panel is outputting into the Sunny Bunny. The second is the voltage of the battery. Third is the voltage of the instrumentation resistor, which we'll later use to get the current coming out of the charging circuit. And the fourth is the temperature of the battery. So we've got LabVIEW set up. It's going to run for a couple hours while we leave this up on the roof to charge. We took 4 key measurements, the first being the temperature of the battery, and we saw that the temperature ranged over 115 degrees, which could be an issue. And when we look at our solar, we can see our solar panel output, which is about 6.5 consistently. It was a very sunny day. We can see the instrumentation current doing the same thing, about 0.6 to 0, a little more frail. And the battery voltage, interestingly enough, it fluctuated all over the place. So what we did is we decided to take another measurement. So we took it the second day, and we didn't have the time to let an LED discharge due to our time constraints. So we did a quick discharge using 10 ohm, 10 watt resistors in series, and we let the battery dissipate into it very quickly. And you can see in half an hour we were able to discharge the battery completely. So then we took it to the roof again, and we measured the roof's data on day 2. And we can see the solar panel output, same as usual. The instrumentation resistor, this time from 0.4, fluctuated a little bit less, going to 0. The battery voltage, interesting, it went from 3.6 to 4 volts, charged all the way. Now, it wasn't at 0. This is probably because the chemicals in the lithium-ion battery makes it sometimes difficult to take the voltage measurements correctly. But we didn't have enough time to take the same amount of study, so this is a 2-hour study instead of the day 1 study, which is longer, and that could have affected our data, but this data looks to be more exact to us, and it goes from 3.6 to 4, which is about 0.4 charging in about 2 hours. So our final product is a solar panel sitting on a roof connected to the charging circuit independent of our lantern. Now, this will be connected via USB, and once the user would like to turn it on, all I have to do is disconnect it from the solar panel and use it.
All right, and so for the starters, we just have whenever the lantern is on, it lights the whole room kind of more broadly, and it acts as a lantern, so you can kind of see the entire space. And then at the same time, you can unscrew the top, and you can see the LED right here. And then this acts more as a flashlight, so you can see forward while you're walking, if that's what the user prefers.
And so overall, we have our finished lantern, and we have on the inside our lithium-ion battery that is charged by the solar panel that Paul pointed out. And we have the USB connection, and we also have a switch. So when you turn the lights off, you can see that the lamp will light a wide range of space.
We recommend the user to keep the LED off while charging because it keeps the charging cycle correct. We also recommend the user to keep the lamp turned out of direct sunlight while charging to avoid the battery from overheating. And lastly, we recommend that the user not charge it to full capacity because it lengthens the life of the battery.
So to start the recommendations for this project, to start we would definitely spend more time with the battery holder, definitely improve that so that it's more sturdy and more robust going forward. Also for a lot of the connections, as in connecting the switch and the USB to the outside of the lantern as well as the LED on the inside, making sure that those are more sturdy as well and that nothing's going to move around. We used a lot of hot glue as far as connections for these pieces, and we would definitely make sure that they fit better. And then the final thing as far as the hardware for this is to make sure that the lantern is more durable. One of the biggest things would be to keep it waterproof, because that would be a really big deal as far as where the location of this would go.
So something else that we would change, if we had more time, it would be ideal to take more data than we did. We were only able to test in certain conditions, like as it was the day that we decided to test. So we were only able to test when it was really sunny or just a little bit cloudy. But it would be nice to know what would happen if it was a little bit more cloudy one day, and things like that.
Okay, to continue off that point, one of the issues we've had is when the battery holder isn't holding it well, it can mess up with our data. Another issue we had was in LabVIEW. We set up automated testing, but one of our main struggles was getting the data to export into Excel with a timestamp already in it. So if we had more time, we would like to re-explore that and not use logic and timing to figure out our data.